Hello everyone, welcome to this tutorial on deep generative modeling for sequential data with dynamical variational autoencoders. My name is Simon Leglève. I'm an assistant professor at Centrale Supélec, a French engineering school, where I work on audio signal processing and machine learning.
Hello everyone, welcome to the tutorial. I am Xavier Lamela Pineda, a research scientist at INRIA in Grenoble, and I am mainly interested in the use of machine learning for computer vision, audio processing, and human-robot interaction.
Hi, I am Laurent Girin, a professor at Grenoble INP, Institute of Technology of University Grenoble-Alpes, and I am also a research scientist in speech processing at GIPSA Lab. GIPSA stands for Grenoble Image, Speech, Signals, and Automation Laboratory.
This tutorial is mainly built from an overview paper we have written with our colleagues Chao Yubi, Julien Diard, and Thomas Hubert. This paper is available on Archive. You will also find on this website additional resources including the slides of this presentation, the implementation of several dynamical variational autoencoder models, and a Google Colab notebook to play with those models on speech signals. This tutorial and its video recording is split into 5 parts. We'll start with an introduction and the necessary technical background, essentially regarding the variational autoencoder. In the next 2 parts, we'll discuss about dynamical extensions of the variational autoencoder. Then, we'll present applications of dynamical VAEs in audio and speech processing. And we will finish this tutorial with a conclusion and a discussion about the VAEs. Between each part, we'll take a couple of questions and we will have at the end a longer Q&A session. So let's start with the introduction and the background. Many successful applications of machine learning, and in particular deep learning, rely on supervised learning techniques. For instance, this video shows a supervised semantic image segmentation method. The goal is here to label each pixel in an urban image according to different classes such as road, car, pedestrian, and so on. This method is built from a dataset called Cityscapes, which contains 5,000 images with high-quality pixel-level annotations. The authors of this dataset mentioned that annotation and quality control required more than 1 hour and a half on average for a single image. It represents a total of more than 300 days of annotation, which is huge even if, of course, it was probably not done by one single annotator. So as we know, annotating data is difficult and time-consuming. And sometimes, for some applications, it may just be impossible. There is a need to go towards more unsupervised or weakly supervised methods, which can learn to unveil the hidden structure of the data without grand truth labels. In this figure is illustrated the result of an unsupervised method called Genesis, which basically also performs semantic image segmentation. It can decompose an image of a 3D scene into its individual constitutive components in a hierarchical manner. The first component corresponds to the floor in the sky, the next 3 components to the individual foreground objects, and finally the walls in the background. This method is not only unsupervised, it's also generative, which means that it can generate new 3D scenes following this hierarchical process. And it is actually based on the variational autoencoder framework. Generative modeling is a powerful paradigm to achieve weakly supervised learning, because it can deal with missing data, represented as latent variables that can be marginalized. In particular, this principle allows us to develop semi-supervised learning techniques where missing labels are marginalized. The goal of semi-supervised learning is to exploit both a small-scale labeled dataset and a large-scale unlabeled one, which is of great interest for many applications. In this tutorial, we'll focus on generative modeling of dynamical or temporal data. So let us first remind the basics of generative models, in particular the ones based on deep learning. We assume that we have access to a dataset of samples that are independent and identically distributed according to some distribution, P star, that we do not know. For instance, it may be a dataset of natural images, and of course we do not know the true distribution of natural images. In generative modeling, the goal is to define a model distribution that approximates the true underlying distribution of the data we observe. Today, we will focus on model distributions that are defined by means of a probability density function, which depends on some parameters, theta. Learning a generative model then consists in estimating the parameters theta in order to make the model distribution as close as possible to the true data distribution according to some measure of it. For instance, minimizing the Cal divergence between P star and our model distribution is equivalent to maximum likelihood estimation of the model parameters. This is the framework that we will consider today. Here is a trivial toy example in dimension 1, where we define the true data distribution P star as a Gaussian distribution with known mean and variance. Of course, this true data distribution is usually not known. We also define the model distribution to be Gaussian, where the mean and the variance are the model parameters. From a set of IEEE training examples drawn from the true data distribution, the blue points in this figure, we estimate the model parameters in the maximum likelihood sense, which is equivalent to minimizing the empirical Cal divergence between the true data distribution and the model 1. We can then generate new samples according to this model distribution, the orange points in the figure, and we see that they are indeed distributed similarly as the training examples. Of course, when it comes to modeling more complex data, typically high-dimensional data, we need more complex models. And for instance, deep generative models. So in deep generative models, the model distribution is somehow defined by means of a neural network, and theta corresponds to the parameters of this network. Probably the two most popular examples today of deep generative models are the variational autoencoder and the generative adversarial network, both introduced in 2014. Deep generative models can contain hundreds of thousands or maybe even millions of parameters, and they can still be trained in a scalable way using large datasets of unlabeled high-dimensional data. You can see on this picture that in only 4 years, the quality of the generated face images using deep generative models, GANs here, has increased a lot. We have mainly 3 types of deep generative models. Autoregressive models define the model distribution using the chain rule. The data, for instance, the pixels in an image of dimension d, are given a specific order, and each individual scalar variable is generated given the previous ones. Deep generative models based on normalizing flow define the model distribution by applying a sequence of invertible transformations to a very simple distribution, such as a unit Gaussian or a uniform distribution. As the transformations are invertible, we can express the probability density function of the model distribution analytically. Finally, we have deep generative models based on latent variables. In these models, we introduce a low-dimensional latent random vector z, and the model distribution is defined by marginalizing the joint distribution of x and z with respect to z. The prior distribution over the latent random vector z is usually very simple, typically a Gaussian with zero mean and identity covariance. And the conditional distribution, which characterizes how the observed data are generated from the latent variables, is parameterized by a neural network. If we want to sample from this model, we first sample from the prior and we pass this sample through what is called the generative neural network. GANs and VAEs are 2 examples of deep generative models with latent variables. but the conditional distribution P of x given z is only defined explicitly for VAEs, as we are going to see. Many works on deep generative modeling with continuous latent variables have considered static data, such as images. But a lot of data are naturally sequential or temporal, such as videos, music, speech, or text. Deep generative modeling for text processing is a bit particular. Text is a sequence of discrete data, and its processing involves natural language processing or NLP techniques. Deep generative models have been used in NLP, but the vast majority of models consider a single latent vector for a whole text sequence, as opposed to a sequence of latent vectors. In this tutorial, we'll focus on continuous valued signals, for instance, speech, audio, videos, or sensor-captured physical signals, for which we may be interested in learning the temporal dependencies between the data, both observed and latent, at different time frames. This means that we will consider a sequence of latent vectors associated with a sequence of observations. Let me now motivate a bit more this ICASSP tutorial and present you the objectives. Since 2014, several papers have proposed extensions of the variational autoencoder to model temporal or sequential data using recurrent neural networks. We cite here a list of the models that we will present in more details later. The general idea behind these models is to combine dynamical models and variational autoencoders. The former being used for modeling the dynamics of sequential data, and the latter for modeling the latent factors of variations in the data. Hopefully, this allows us to develop models that are more expressive than both classical dynamical probabilistic graphical models, such as the state space model, and standard recurrent neural networks, including their gated extensions. So, the objectives of this tutorial are the following. First, in a unified framework in terms of notations and presentation structure, we will discuss representative temporal extensions of the VAE that were proposed in the literature, mainly in the machine learning one. Second, we will introduce a general class of models that we call dynamical VAEs, and that encompasses the above-mentioned models into a general methodology. Finally, we will show some applications of dynamical VAEs for audio and speech processing. Now, I'll let Xavi continue with the background on variational autoencoders.
Hello, my name is Xavi Lamela Pineda, and I will take over this introduction by discussing the plain variational autoencoder. Variational autoencoders are nonlinear generative models that attempt to model the distribution over the observed variable x that has dimension d. And to do that, they assume that this distribution is the marginal over a joint distribution of this observed variable x and a latent code z that has much lower dimension k. Differently from other simpler models, this marginalization operation, so this integral that you see on the slide, cannot be computed because the likelihood, so this p of the observed variable x given the latent code, has nonlinearities in it, and therefore this overall integral cannot be computed in closed form. More precisely, in VAEs, the prior distribution of the latent code z is assumed to be a standard multivariate Gaussian distribution, and the likelihood, meaning the conditional distribution of x given z, is assumed to be parameterized with what we call a generative network or the decoder neural network. More precisely, we assume that the likelihood is a normal distribution whose parameters, meaning the mean and the covariance matrix, are computed by the decoder. So this decoder, as you can see on the right, inputs the latent code Z and outputs mu and V, which are the mean and the variance of the distribution of X. And in order to compute this, it's using a neural network that is parametrized by theta. The direct estimation of the parameters is very difficult because the marginal likelihood is intractable, as we discussed in the previous slide. So direct maximization is very, very difficult. Luckily, we have the following statement that tells that for any distribution, any conditional distribution of the latent codes given the observations, we can write this expression. So on the left, you have the quantity that we want to maximize, which is the log likelihood of the marginal distribution. And on the right, you have this L that is called evidence lower bound or variational lower bound. And we will discuss about this later. And the Kalb-Laguerre divergence between this arbitrary posterior distribution on Z and the true posterior distribution of Z given X. One can easily verify that the evidence lower bound actually writes as the expectation of the difference of the logarithm of the joint distribution and the posterior distribution, as you can see here written on the slide. In the expectation maximization algorithm, this quantity is also referred to as the expected complete data log likelihood. And we alternate between minimizing the Kalb-Laguerre divergence that you have in the first equation and maximizing the evidence lower bound. Because the true posterior distribution, this p theta of Z given X, cannot be written in analytical form in VAEs due to the very same nonlinearity, this Kalb-Laguerre divergence term is dropped and ignored, and this is why, because this DKL term is non-negative, this is why L is an evidence lower bound or a variational lower bound. We have now two problems because we need to maximize this lower bound with respect to both the parameters of the decoder or generative model and the parameters of this arbitrary distribution Q phi. While maximizing with respect to the parameters of the decoder, we are pushing a lower bound on the log likelihood, and then hopefully as soon as this lower bound becomes tight, we are pushing as well the log likelihood, which is our initial objective. But at the same time, we need to maximize this lower bound with respect to the parameters of this arbitrary distribution, and by doing that, because the log likelihood does not depend on these parameters, we are implicitly minimizing the Kalb-Laguerre divergence that we cannot write analytically because p theta of Z given X does not exist. In other words, problem 2 is minimizing the margin between the log likelihood and my lower bound. And then in problem 1, I am pushing this lower bound. So by maximizing with respect to the two sets of parameters, theta and phi, I am actually getting this lower bound tight to the log likelihood and pushing the lower bound, and therefore, hopefully, the log likelihood as well. In the extreme case in which the lower bound is tight, so that means that this inequality is an equality, this automatically implies that the Kullback-Leibler divergence is 0, which means that the arbitrary distribution Q phi is exactly the posterior distribution P theta. This is a point that is very difficult to reach, and most of the times we don't reach, but it also gives us an intuition on how Q phi should be. So Q phi should approximate the posterior distribution as much as possible. So now, in order to fully define the objective function to optimize, we need to actually define this inference model or approximate posterior distribution Q phi. We will use the very same strategy that we used in the decoder, but inversing the role of X and Z. Indeed, we will assume that Q phi follows a multivariate Gaussian distribution whose parameters mu phi and v phi depend on X through a nonlinear neural network that is also called encoder. So this encoder inputs X, applies a series of layers and nonlinearities to finally compute mu phi of X and v phi of X, which are the parameters of the approximate posterior distribution, or also called the inference model. Now this allows us to write the full evidence lower bound or variational lower bound, which is this equation that you have on the top. If we develop this a little bit, we can split the expectation into two terms that are, of course, two different expectations. The first term is usually referred to as the reconstruction term because it is supposed to give an estimate of the reconstruction accuracy of the method. And on the right, we have a Kullback-Leibler divergence that it is regularizing the posterior distribution to be close to the prior distribution of Z. Just as a reminder, we have a prior of Z that is a standard normal distribution, a good model which computes the parameters of the multivariate Gaussian distribution on X from the input Z, and the inference model, which is the opposite, computes the parameters of the multivariate distribution on Z from the observation X. Here on the right you have the full diagram of the variational autoencoder. We input X to the encoder that computes the parameters of the inference model or the approximate posterior, which is mu phi and v phi. Then we have a sampling operation that we will discuss in a short while. This gives us one value of the latent code that is input to the decoder that outputs the distribution of X given Z tilde in this case. So the reconstruction accuracy, so this expectation on the left cannot be computed in closed form due to the nonlinearity of the decoder, and therefore it is approximate with a Monte Carlo estimate, which means in practice that we draw samples from the a posterior approximation, which is Q phi, and then we approximate the expectation with an average sum of the likelihood given this set of samples. A difficulty when doing this is that the sampling operation is not differentiable with respect to the parameters of the encoder, so we could not backpropagate the error through the encoder because the sampling operation is not differentiable. To overcome that issue, we use the so-called reparameterization trick, and we realize that sampling directly from the distribution Q phi is equivalent to sampling from standard normal distribution and then applying the operation that you see on the second line. The huge advantage of doing that is that now we decouple the sampling operation, which is non-differentiable, from the parameters of the encoder or the inference model, and therefore we now can backpropagate not only through the parameters of the decoder, but only through the parameters of the encoder, because the sampling operation is decoupled. So just to give an overview of the entire training procedure, we assume, of course, that we have the prior P of Z. Here is in green. So these are in green. We will show the mathematical objects that are already given or computed. And on red, we will have the mathematical objects that are our interest at every step. So the first step, of course, is pick an example in the dataset, an image, a vector, a sound. Then we forward this through the encoder. So this allows us to compute the parameters of Q phi of Z. This is why Q phi is in red. These parameters are mu phi and V phi, the mean and the covariance matrix. Once we have done that, we can sample Z using the reparameterization trick that I explained in the previous slide. This gives us Z tilde, which is one sample following the approximate posterior distribution of Z given X. This sample is then given to the decoder that is computing the parameters of the likelihood or the conditional distribution of X given Z tilde. And once we have done that, we can compute the loss shown in the previous slide and take the derivative with respect to both the parameters of the encoder and the decoder, and therefore backpropagate the error through the entire network. A priori, we do not need the encoder once the training has converged. Indeed, we have introduced the encoder to approximate the posterior distribution so that we could learn the parameters of the decoder, which is our object of interest. The decoder here, theta, are the parameters of the generative model, which is what we wanted to learn in the first place. In order to generate new samples, we don't need the encoder either. We can just sample from the prior distribution of Z, the standard normal, forward through the decoder that provides us the parameters of the conditional distribution of X given Z tilde, and that allows us to sample from those parameters. So we can, once the learning is done, we can generate new data without using the encoder. However, as we will see later, this encoder can be useful at test time if we need to do some inference. For instance, when we need to combine the generative model with other probabilistic models. VAEs have been applied to a wide variety of learning problems. Here we give a few references to the use of VAEs in audio and speech processing. For instance, in modeling and transforming speech signals, synthesizing speech signals and music, and then when used for single channel or multi-channel speech enhancement and separation. We encourage you to go and take a look on how the VAEs are used for these tasks in case you're interested. So this gives a quick overview of the methodological details behind the variational autoencoders, and we will now discuss one of their limitations, which consists on modeling sequential data. Indeed, we have seen how VAEs are very popular for generating samples, and by samples I mean independent samples. So in here you have MNIST, or the very recently Nouveau VAE that generates high quality phase images. But in here, each of the digits or each of the phases is considered as one sample. And therefore, there is no relationship, there is no statistical relationship modeled between samples. And this is what we call static data VAs. However, a very natural question is what happens when we want to model sequential or temporal data. And a very clear example of such data are speech signals. So here we will hear first the original signal.
Ok Vesta, je veux augmenter la lampe du salon progressivement.
And then the reconstructed signal of a VAE that was designed for speech, trained on a very large data set of speech, and then reconstructed using the DVAE for the magnitude of the spectrogram, and then using the original phase of the spectrogram to add on the phase to the reconstructed magnitude.
Ok Vesta, je veux augmenter la lampe du salon progressivement.
So we can hear and understand well, but we also need to keep in mind that this is an analysis resynthesis task. So we are inputting the original signal and asking the VAE to reconstruct this signal. If we now want to generate from scratch a speech signal that is from the very same VAE that was used in the previous slide for reconstruction, we can quickly understand that has nothing to do with speech. And also from the image we see that there is no temporal consistency whatsoever. We tried the very same experiment with a DVAE.
Ok Vesta, je veux augmenter la lampe du salon progressivement.
And the reconstructed signal.
Ok Vesta, je veux augmenter la lampe du salon progressivement.
Which is much better than when the speech was processed each frame independently, as in the case of VAE. And when we try to generate, we can see that even if we don't understand much, because this is complete random generation, we can identify several things. We can identify the structure as phonemes. We can identify voiced and unvoiced phonemes, and also effects that are proper to speech, such as co-articulation and silences. You can also see this by comparing the spectrogram that you can see in the slide with the previous one. It is quite obvious that this one has structure. So even if we cannot understand what is generated randomly by the VAE, we can see that the data patterns are much more faithful to the original data patterns of speech than when the very same experiment was run with a VAE that processed each frame independently. In the following, Laurent will formulate the problem of sequence modeling and learning and explain the models that allow to do that to finally go to the dynamical VAEs.